So now we know those two optimality conditions. Now we know that this is a very quick summary. When we minimize f over a convex feasible region capital F, if our small f is convex, we actually only need to search for a local minimum. Or if our small f is concave, we only need to search among extreme points. And then maybe you already see it. If we are talking about a linear program where our f is either convex or concave, and then we have both. So first, maybe I need to remind you about how a linear function is both convex and concave. So when you are talking about a convex function, we need the cutting point, the line segment, to lie above the function values. Okay, and of course, for above, we mean the equality is acceptable. So for concave, is somewhat similar. We need the functional value to be above your line segment. And again, here, equality is okay. So if you have a linear function, then for any 2 points that you may get to do the connection, that particular line segment is above that particular function and below that particular function at the same time. So that's why we say we have both. So if we have both conditions, then that's why for a linear program, a local mean is a global mean, okay? And we only need to focus on the extreme points. So that's how this helps us verify what we have done with the simplex method or other things somewhat make sense. For the simplex method, we always go along extreme points. We only focus on extreme points. And once we are done with a point where there is no way to improve, we say we are at an optimal solution. Okay, so that's why the simplex method works in that way. So maybe we want to go through some rigorous proof. So first, we need to show that the feasible region is convex. So if that's the case, well, let's consider the feasible region of a linear program, which is the intersection of several half spaces. Okay, here, there, something like that. So it is trivial to show that half spaces and half planes are always convex. I think we all agree with that. It seems so true. And remain to show that the intersection of convex sets are convex, which is left as an exercise. So what does that mean? This is saying that if you have two convex sets, then their intersection would also be convex. Okay? I think that makes sense because if you take 2 points in their intersection, then it's going to have the line segment completely lie in the first set, also in the second set. So it should also lie in the intersection, right? So just try to write down the proof a little bit by yourself. It shouldn't be too hard. Then also, this is another thing we mentioned. A linear function is actually both convex and concave. So the idea I just drew the picture for you is that we have a line segment, then it lies also above or below that particular original function. So algebraically, we may still do derivations. What we need to do is to show that when we have 2 points, if we get their functional values and connect them, okay, we need to have equality for all other cases where we first combine them and then do the functional plugin. Okay, so if we want to show that, then it's not really too difficult, right? Because our f function may be expressed as C transpose multiplied by your x value, plus some constant that we don't really care. This is because a function can be expressed as C transpose x plus b if your function is convex. Okay, so once this is the case, then everything is separable. So you may take lambda outside and 1 minus lambda also outside. You're going to get lambda multiplied by C transpose x1 plus b plus 1 minus lambda times C transpose x2 plus B. And then this is f of x1, this is f of x2. Nothing really difficult. So that's how a linear function is both convex and concave. The key is that a linear function is separable. So to solve an LP, as we just mentioned, a greedy search focusing on extreme point makes sense and works and guaranteed to give you a global optimal solution. That's why the simplex method always gives you an optimal solution. As long as you follow the simplex method, it guarantees to give you that very special local mean, which guarantees to be a global mean and lie on an extreme point. Okay, so that's the simplex method. So we don't really always work on linear programs. For most of the cases, when we talk about NLP, it's not linear. Okay, so now we define one concept called convex programming. If we have a nonlinear program like this, and then if the feasible region, which is the intersection of all these regions satisfying these constraints, okay? So if the feasible region is convex, and the small f, the objective function, is also convex over the capital F, then a local minimum is a global minimum, okay? This is something that we would heavily rely on in this particular lecture or course. Pretty much it says that what we need is to have a convex program, all right? This is something we already know, right? So all we need to do is to give it a definition. So a nonlinear program is a convex program if the feasible region is convex and the objective function is convex over the feasible region. So that's the definition of convex program. So one thing I would say is that in many cases, some people also take a look, consider a maximization problem. So for a maximization problem, if your feasible region is convex and you are maximizing a concave function, we also say you are doing convex programming. Okay, so there's no such term called concave programming. No, we only have convex programming. We are minimizing a convex function or maximizing a concave function subject to a feasible region that is convex. Then we say you are doing convex programming. Okay, so I guess it is easy to convince all of us that if your program is convex, then global mean can be found by looking for local mean. So efficient algorithms should exist. Gradient descent, Newton's method, and many other methods that we have no time to teach you. These methods should exist for solving convex programs. So if we are talking about formulating and solving convex programs, that subject, that field is called convex programming. So sometimes we would need to show that a set is convex or to show that a program is convex. How may we do that? In many cases, we need to focus on this particular set of constraints. Okay, so the thing is that if your f is a convex function and all your g functions where g is at the left-hand side of a less than or equal to constraint, if all your f and g are convex functions, then your nonlinear program is a convex program. So what does that mean? Let's take a look at the proof so that maybe you would get some ideas. Basically, if f is convex, then we are done with part of the condition. So now we only need to prove that the feasible region is also convex. So we are talking about the fact that we need to show that the set fi given by a convex function g in this way is convex. So if each constraint gives you a feasible region which is convex, then their combination would, intersection would also be convex. Okay, so we now only need to focus on this fact. Okay, we want to show that as long as your GI is convex, then the corresponding Fi, the set, would also be convex. So this can be done. All we need to do is to apply the definition. If x1 and x2 are in Fi, then we know we want to have this particular inequality, right? Then we can take a look at x1 and x2. We now have a convex combination and we put that into the G function. The interesting thing is that if we know that this particular thing is true, where your G function is convex, then in this case, if you split this convex combination to two functional evaluation and then do the combination, we all know that according to convexity, we have this inequality. Okay, so I hope that makes sense. And also, we know your G and GI of x1 is less than or equal to bi. GI of x2 is also less than or equal to bi because they are in the set. And then this combination gives you bi. So what does that mean? This means the new point that is obtained by doing a convex combination satisfies this G of something less than or equal to bi constraint. So that point also lies in the set. And then you know Fi is also convex. Okay? So each convex function formulated in this way is going to give you a set that is convex. So if you have the intersection of all these sets, it's also convex. And then we're done. We have a convex program. So let me give a quick conclusion of this particular section. We have learned a lot of algorithms in the past, right? Gradient descent, Newton's method. At that moment, we have no way to check whether the reported solution is really globally optimal. All we know is that, well, it shouldn't be too bad. But now we should be convinced that we actually may efficiently solve those convex programs, because convex programs, they have nice properties. Local mean is global mean. So searching for local mean is not too difficult. People can do it. Even if you have a lot of constraints, as long as it's a convex program, it's fine. On the other hand, if you have a general nonlinear program, which is not a convex program, then people really don't have a specific way to do it. So later, we will focus on how to analytically solve nonlinear programs, and we will see those analytical solutions are the foundations to give us some managerial insights.